This assessment asks us to give the mechanism of the acid-catalyzed aldol reaction shown on screen. It's intramolecular as well. Now, I'll go ahead and warn you, this is a long video. You probably know that by looking at the timestamp, and it has to be. Why? Well, because the intramolecular aldol has lots of steps, and when you make it acid-catalyzed, it has even more, because we know that we're going to have lots of protonation, deprotonation steps. So at the end of this mechanism, it's going to look like one of the more complicated reactions we've ever done, but it's because we have lots of acid-base reactions interspersed between the important bond-forming reactions we're used to in the enols, enolate chapter. One of the things that I had to do in making this video is I'm going to work to here. We're going to do the first half of the reaction, then through the magic of computers, we're going to wipe all that out and finish. That way we can see all of it on the screen. So it gives you an idea of all the things that we're going to have. We're going to actually have to cut it all out and finish the reaction. But I think it will make it a smoother video. How do I know that? Because I already tried to do it the other way once, and this is where we're at. So how do we start this reaction? We start by numbering the carbons, and I've gone ahead and done that on screen. Very quickly, how did we know what these numbers were? Well, we started just with this molecule on the left, just numbering 1 through 12, right? We can't really make a mistake there. But when we transfer the numbers over here, that's where mistakes can be introduced. How do we avoid those? Well, the keys here are carbon 4 and carbon 9. Carbon 4 and carbon 9 are the juncture of the ring, and so we know that these two are these, so that must be these. Well, to get from 4 to 9 going counterclockwise, we go through 5, 6, 7, and 8, 5, 6, 7, and 8. So we're pretty confident about those numbers. The other reason we're confident about those is 5, 6, 7, and 8 are CH2s in the reactant, and they're CH2s in the product. So no chemistry has happened to those. We feel pretty good that we have those numbered correctly. And that gives us a common way of doing that is look for the things that don't change. So for example, carbon 4 is attached to carbon 3, which is a CH2. We have a CH2 in the product. That probably is carbon 3. It's attached to 2, which is attached to 1. 1 is an aldehyde, 1 is an aldehyde. Now 2, something's happened at 2, right? 2 was a CH2. Now it has formed a new carbon-carbon bond. Well, that tells us that that's where the chemistry has happened. But because we know all the other atoms are numbered correctly, we can be pretty confident that that's carbon 2 and is where chemistry happened. The same thing we can do on the other side. Carbon 10 is still a CH2. Carbon 11 is still a CH2. Carbon 12 is no longer a CH2. It was an aldehyde, or it's not a CH2. It was no longer an aldehyde. It's now a carbon-carbon double bond. Something has changed at carbon 12, so we're doing chemistry there. Given that we know that this is an aldol reaction, what chemistry is happening? Well, we're forming new bonds between carbon 2 and carbon 12. Not just one, but two, a single bond and a double bond, or a sigma bond and a pi bond. Which makes sense, because in the aldol reaction, when we heat it, we drive off, we eliminate water or hydroxide at the end, so it would make sense that we would form that carbon-carbon double bond. Right? Just by doing that analysis, we see that we're going to really be focused on forming the carbon 2, carbon 12 bond, which is what the aldol reaction, we have an idea of how we're going to do this. Now, in the aldol reaction, typically what happens is we make a nucleophile at carbon 2, at alpha to a carbonyl, and it attacks some electrophile. Well, we can make an enol, not an enolate here. Why not? Because we're under acidic conditions. So enolates have negative charges. We never want to make a negatively charged species in the presence of acid. So we're going to make an enol, which is a good nucleophile, at carbon 2, and have it react with the aldehyde at carbon 12. Now, enols are neutral nucleophiles, so we're getting ahead of kind of laying out our strategy here. Enols are not great nucleophiles. They're good enough, but they're not going to react with a neutral aldehyde. So in order to get the aldehyde to react, ultimately we're going to need to protonate it. So we know by identifying the bonds formed and bonds broken, the carbon 2-12 bond that we're going to form, we know we're going to make some nucleophilic species at 2 and something electrophilic at carbon 12, and we're going to use acid to make that happen. So looking at the reaction, sulfuric acid and water are going to combine to make H3O+, and we're going to start by making the enol. So we need to make the enol at carbon 2. We'll do that by first protonating the carbonyl. Okay, I'm going to use lots of space, so I'm going to go ahead and write in front of me. I know that's not perfect, but we kind of need to do that. So we'll start by drawing the protonated aldehyde. And when we draw that protonated aldehyde, we won't put the numbers in. We're going to live on the edge and keep it unnumbered just for a second, but eventually we'll put those numbers back in to make sure we haven't made any mistakes. But we protonate the aldehyde at carbon 1. The next thing we need to do to make the enol, we have 2 protons, 2 hydrogens at carbon 2. We need to remove one of these to complete formation of the enol. So we can show a molecule of water coming in and removing that proton and pushing those electrons to form a new carbon-carbon double bond, which pushes the CO pi electrons onto oxygen. That will give us our enol at carbon 2. We're using equilibrium arrows here because all of these reactions are reversible. So let's draw the enol at carbon 2. So here's carbon 1, carbon 2, and we know that carbon 12 is our aldehyde that's going to be our electrophile. Now, we mentioned earlier that enols are good nucleophiles, but they're neutral, and we learned previously that aldehydes don't react directly with neutral or weaker nucleophiles. So we need to turn that aldehyde into a better electrophile. Well, good news, we've got acid present in solution, so we can use the acid to protonate that aldehyde and make a better electrophile. And so we'll have that react with H3O plus again. We still have H3O plus around because it's catalytic, and we actually reformed H3O plus in doing the enol step, or in our final formation of the enol step. So we can draw all of that together. We'll put our enol here, count over to our 6-membered ring. That's a wedged bond here, up to carbon 12, which is now protonated. Let's go ahead and put in all of our numbers to make sure we have this right. So the 4, 9 was the ring juncture, 5, 6, 7, and 8 are unchanged, 10, 11 are unchanged CH2s. Our numbering still works out, so we haven't introduced a mistake in this complicated reaction. Well, what are we ready to do now? We're ready to make the bond between carbon 2 and carbon 12. And so the way that's going to happen is the enol, the electrons on the oxygen of the enol are going to collapse down to form a new carbon-oxygen double bond, pushing these pi electrons out. They're going to come over here and attack carbon 12, pushing those electrons back onto the oxygen of the protonated aldehyde. This is where it gets a little bit tricky because now we've done this intramolecular reaction, and we know that drawing the ring can be difficult when we do that, but we have our carbons numbered, so that's going to help us out. We also have our product, right? We see that we're going to make a 7-membered ring, and that bond is going to be formed between carbon 2 and carbon 12. If we count over 2, 3, 4, 10, 9, 10, 11, 12, that's going to make a 7-membered ring. And so we know that we can kind of just draw our 6-membered ring here, draw a 7-membered ring on top of it, and we should be getting on our way to drawing the right structure. The other thing we can do is let's draw it in a similar form to what we have over here. So let's go ahead and draw our 6-membered ring, 4, 5, 6, 7, 8, and 9, right? That's unchanged, so we know that's going to be that. At carbon 4, we're going to go up to carbon 3, over to carbon 2. That's going to have our new bond to carbon 12. Carbon 12 is attached to carbon 11 to carbon 10, and carbon 10 has that wedged bond from carbon 9. We've made our 7-membered ring. We've kept true to the fact that we're making a bond between 2 and 12, so we've made our 2-12 bond. All we need to do now is decorate the molecule, decorate the ring that we've made. And so we can do that at carbon 2. We have the aldehyde. These electrons collapse down to make that new carbon-oxygen double bond. We still have the hydrogen hanging out here, and we still have the proton on that oxygen, so that proton has not fallen off. At carbon 12, we have a hydroxyl group. All that remains to complete the first part of this reaction, the aldol without elimination step, is to remove this proton. And so in a final step, we'll have water remove that proton to give us this product. keeping the numbering, right? To make sure we want to make sure we don't make mistakes in these long, complicated mechanism problems. It's really easy to make a mistake by leaving something out, but if we keep everything numbered, we're less likely to make that mistake. So 2 is attached to 12, 11, 10, 9, 4 to 9. We go through 5, 6, 7, and 8. This completes the first half of this mechanism. And I'm going to pause here for a second, and when you come back, all of this will be gone so that we can then finish the problem working in this direction. And welcome back. Let's think about what we have left to do. Well, we've got this product here, and again, we're still thinking about where we're going here. If we draw on the hydrogen, you'll notice that at carbon 2, we still have a hydrogen, but this carbon 2 does not, so we're going to lose a hydrogen there. Carbon 12 has a hydroxyl group. Carbon 12 does not. We're going to lose that. And we're going to make a double bond between carbon 2 and carbon 12. So we can think, right, what looks like is about to happen is we're going to do an elimination reaction. Now, if it were as simple as an E2 elimination, we could draw one set of arrows and get us to here, but we can't. We're not in basic solution. In fact, we're in acidic. Hydroxide is not a great leaving group. How do we make it a better leaving group in acidic solution? We need to protonate it, okay? So the first thing we know we're gonna need to do is we're gonna need to protonate this to make it a better leaving group. The other thing we're gonna need to do is we're gonna need to remove this proton. Well, water's not a strong enough base to just remove that proton. And so how are we gonna do this? Well, what's gonna need to happen is we're gonna need to make an enol over here so that we get that double bond. That's gonna be what ultimately kicks off the protonated water molecule. So we're in that situation again where we need to convert this side into the enol and this side into a good leaving group. Let's make the enol first. So this is going to look a lot like what we did in the early stages of this reaction, where we're going to protonate this oxygen with H3O+. The good news, at least going forward, is we have the molecule in basically the structure that we want it to be. So it's going to be a little bit easier, or we can draw a little more quickly each of these molecules, because we basically can just keep everything the same. So we'll protonate the aldehyde. We can now remove this proton to complete formation of the enol. At any point, you may want to do a check to make sure we're in the right numbering. 4, 9, 5, 6, 7, 8, 3, 2, 12, 11, 10. Pretty good there. Put the hydroxyl group in. We've created the enol, which if we were under base conditions would be an enolate. We could now kick off the hydroxide, but hydroxide is not a great leaving group. We need to make it a better leaving group. We've got acid around to do that. So let's protonate that using, again, H3O+. Notice we keep doing a bunch of acid-base reactions. We keep regenerating water and H3O+, H3O+ being the catalyst. That's going to get us to here, and we're going to start to get close to the finish line of what is almost certainly the longest of these YouTube videos, or the longest of these solution videos. Keep the numbering, make sure we have that, 12, 11, 10. And that gets us to here. So we've got a nucleophile, or a pi electrons at carbon 2 that can push out that leaving group, which is very good, water. And it can actually be assisted by the lone pair of electrons on oxygen. So these electrons can come down, push these electrons over, and kick out the good leaving group. That's going to get us to a molecule that I'm going to have a tough time getting out of the way of to draw, but if I move over here, our aldehyde at carbon 1 still has the proton attached. While I'm drawing, think about how we're going to remove that proton, because that's the last thing we're going to need to do. Put in our wedge bonds. That's 4 and 9 connected to each other through a 6-membered ring. So 4, 9, 5, 6, 7, 8. This is the last molecule we'll have to draw. So let's number the carbons one more time. Carbon 1. We've eliminated that. We formed a new carbon-carbon double bond. That's there. We formed a new carbon-oxygen double bond. That's there. Oxygen still has a proton. We are almost done. All we need to do is remove that proton to make this molecule. Good news. We have water present in solution. So our water molecule can remove that proton, pushing those electrons to oxygen, and that's going to get us to the final product. Most satisfying arrow, we're going to draw it. It's going to look, let's make sure we find the space to draw it, is from there, and then it's reversible. So we will do that, but that gets us to our final product. This is the mechanism of the acid-catalyzed intramolecular aldol. If you're still watching, thanks for your patience. I hope the splitting it made it easier and smoother for you to follow.